All right, kiddo. So today we talked a little bit about the extreme value theorem, and that's a nice little theorem that essentially guarantees us a min and max as long as the function is well behaved on some closed intervals. And by well behaved, I mean continuous. Right? So as long as the function is continuous on some closed interval, there's got to be a max and minimum value. So that said, let's go about figuring out how the heck we use the first derivative to find those min and max values, those extreme values. So here's what we're going to do. We're going to look at this function right here, and it's 3x to the fourth minus 4x cubed. Nice, easy example. Here it is in blue. I've already taken the liberty to graph it. And what we're going to do is we're going to look at this particular function on the closed interval -1 to 2, right? So -1 somewhere over here, and 2 is somewhere up here. Okay, so here's -1-ish, and there's 2-ish for x value. So first of all, recognize that the extreme value theorem does apply to this function, which is continuous on this closed interval, right? So we know there's got to be a min and max. The question is, how the heck do we find it, right? So let's go about finding those min and max values. Now, if you ignore the derivative, which I already graphed in red, just in the interest of time, the min is pretty easy to see, right? The minimum value is right here, that valley, right? So all we have to do is go about finding it. Now, truth be told, all we can certainly do, one way to find that minimum value is just use our calculator, right? The calculator has that capability. But there's some good calculus theory behind it that we're going to think about to find that minimum value nonetheless. The maximum value appears to happen somewhere probably at 2, right? Here's 2, the y value, and here's -1, the x value. Right, x value -1, x value 2. So the question is, where on earth is the maximum value? So it looks like the minimum's here, and I would guess that the maximum is at 2. Right. So that said, let's go about finding the minimum value, really using the first derivative. So what we're first going to do is use what are called critical points to find where we could potentially have min or max values. So here's my derivative coming up. It's nice and easy enough to get, starting with a nice easy example, using both the coefficient and power rule. So it's 12x cubed minus 12x squared. And if I so choose, I can just factor out 12x squared, and we're left with x minus 1. Okay, so there's my derivative. And what I did was I graphed the derivative here in red on the same Cartesian plane as a function, the blue one, which we're trying to analyze. We're trying to find extreme values. Right? So first recognize that something important is happening, or could potentially important, when the derivative equals 0. Right? We have what are called horizontal tangents. So it looks like we're going to have a horizontal tangent on the blue function around 0 and around this right here. And that's the money maker right there. That's what we're looking for. But we're also in this analysis, we're going to dust up the critical point around, or at, 0. So let's backtrack. Critical point is where we could potentially have a max min. And for now, those critical points are when the derivative equals 0. So critical points, in this case points, is when the derivative equals 0. And here's my derivative. So that gives me what? X equals 0 comes from this factor, and x equals +1 comes from that factor, right? So those are my two critical points. Critical points are, for now, points at which we have horizontal tangents, which are potential max min values, or where really potential max values could occur. Right. Another version of a critical point is really where we have a point of non-differentiability. But for now, critical points are just where the derivative equals 0. We're trying to isolate those horizontal tangents and hope that they're going to yield max min values. So what I'm going to do is I'm going to now verify that those critical points either are or are not min or max values. So the way we do that is we can certainly look, and of course on the blue function there's not a min or max at 0, but there is a min at 1. Right? So here comes the calculus. So what I'm going to do is I'm going to structure a chart, and a chart is a good way to organize this information about my critical points. So there are the critical points, values of x, and I'll put a 0 here and a 1 here. And we're going to use that chart, values around those x values, to take a look at not only what our derivative is doing, but that's going to help us evaluate what our function y is doing. Right? And that's what we're trying to do. We're trying to analyze this function y, the blue function. Right? So what I'm going to do is I'm going to take a look at these critical points. And we already know those are points at which the derivative equals 0. But the question is, what's happening around those critical points? Because that's what's going to give us what we're looking for. So what I'm going to do is on the up until 0, I'm going to look at the derivative, right? Here's my red derivative. And up until 0, it happens to be negative, right? How do I know it's negative? It's below the x-axis, right? So up until 0, the derivative is negative, which means on that same interval, my blue function, which I'm analyzing, is decreasing, right? Negative derivative below the x-axis, decreasing function, right? So that's some good information to know, right? So up until 0, x value of 0, my function is dropping, right? That's noted by this graph. Okay, at 0, I have a horizontal tangent, right? And then what's happening between 0 and 1 is my derivative is still negative, right? How do I know it's negative? It's below the derivative of the x-axis, right? So when the derivative is negative, that means that my function, which I'm analyzing, will be decreasing over that very same interval, right? So what does that help me find at 0? Well, at 0, I have a horizontal tangent because that's where the derivative equals 0. But what's happening at 0 on the function, as you can see, is there's no change in behavior of the function. It's decreasing, stopping momentarily, then decreasing more, right? So that doesn't make this point 0 a min or max, even though it is a critical point, right? It's a point at which the derivative equals 0. So all we have at 0 is a plain old horizontal tangent, right? Neither a min nor a max, because we have no change in behavior in the function, decreasing to decreasing, which is noted by no change in sign of the derivative, negative to negative. Okay? However, something interesting does happen after, really at 1, and then therefore after 1 too. So what's happening is here is 1, right? That's the value of 1. And this 0 of the derivative, right? The red function's derivative corresponds nicely to the what ends up being the horizontal tangent of the function, right? Same thing is happening at 0. It's hard to see because they're on top of each other, but it's easier to see that the derivative at 1 is 0. That's a 0.10 on the derivative, and therefore the function at 1 has a horizontal tangent, right? So what's happening after 1 on the derivative is it's positive, right? How do I know it's positive? Because it's above the x-axis. So whenever the derivative is positive, that tells me when the function, which I'm analyzing, is increasing, right? Positive derivative means positive slope, which means an increasing function. Oh, there's that nice bell. So what do I know, therefore? Well, I know at 1, even though we have a horizontal tangent, we have more than that. In fact, we have a minimum. And I know we have a minimum because at 1, this point right here, that's where the function is changing from decreasing, stops, horizontal tangent, to increasing. Right? So there's my max that I'm looking for. Excuse me, my min that I'm looking for. Right? The minimum isn't 1. The minimum just happens when x is 1. Right? The x value of that minimum, that valley, is 1. Right? So how on earth do I find the minimum? So I know so far there's a minimum at x equals 1. Right? So I find the minimum simply by plugging the 1 back into the function. Right? I know there's a minimum here. I know what the function is. I know the x value, so I can get the y. Right? So I plug a 1 back in for x into the original function, and I get, what, 3 minus 4, which is negative 1. Right? So at the end of the day, negative 1 is the y value, therefore the minimum of this function from on the interval negative 1 to positive 2. Okay, so I got my minimum. It's negative 1. Where does it happen? When x is 1? Right here. Bam. Okay, so the extreme value theorem also guarantees me a maximum, right? I haven't found that yet. This horizontal tangent at 0 is not a max. That horizontal tangent is not a max. So neither of those two critical points bear min or maximum. There's got to be a min or maximum. Oh, where's it going to happen? Well, we're given a closed interval, so it therefore has to happen at one of the endpoints, right? So where's the max? Well, the max has to happen at one of the endpoints. It's not anywhere in the interior of that interval, from negative 1 to 2. open interval. So it's got to be at either negative 1 or 2. So all I'm going to do is I'm going to plug in negative 1 to the function. And when I plug that back in to the original function, which is this blue function, negative 1, I'm pretty sure I get 7. Yes. Right? I'm going to compare that to what I get when I plug in a 2. And when I plug in the other endpoint, right? So we're going from negative 1 to 2. Here's one endpoint. Here's the other endpoint. When I plug in positive 2 into the function, I get a y value of 16. My positive 2 is going in for the same x to that function, 3x to the 4th minus 4x cubed. Right? So here around is negative 1, 7. Way up here is a point 2, 16. And my other minimum value, my only minimum value really, is negative, well, excuse me, 1 comma negative 1. Right? So minimum value, negative 1. There's got to be a max. Since 16 is greater than 7, my maximum value is 16. It happens way up here at x equals 2, the right endpoint of the original closed interval. All right? So in conclusion, we're using the first derivative to find and verify min and max values. What's up, Kareem? Give me a shout out. Right? This chart is a way to organize that information, the theory behind what we're doing, which isn't all that difficult. Most people say, oh, just look at the graph. There's your minimum, and your max has got to be somewhere up here. Right? And that is true. But here's the calculus that verifies that. That's what we're thinking about. All right? Have a good day. Come in with questions tomorrow. See ya.